So we saw in the previous videos where we were approximating limits using tables that it's kind of an estimate. You can't tell me exactly what a limit is by looking at a table. And so we're going to look at it another way to estimate limits. And again, it's just an estimate. We're going to use graphs. So I've got a graph of a function given here, and I've got several different limits I want to compute. First one is I want to find the limit as x goes to 0 of this function. And so what that's saying is, as I let my x values come in towards 0 from either side, you can see that this graph is headed towards, looks like 0. So for this first one, I would certainly say the limit as x goes to 0 of f of x appears to be 0. Now again, it's just an estimate. Maybe it's 0.1, we can't tell, but it looks like it's going to be somewhere really close to 0. And so that's the geometric way of looking at it, where the graph is going is as we let x go to 0 is what we call the limit. Now this is a little bit different. We've got a little minus sign there, and what that means is I want to take the limit as the x coordinates, the x values go to 2, but from the negative side or from the left. So that's what the little minus means, and here's a little plus on this one. That means I want to know what happens as x goes to 2 from the right. So I'm looking here. The first one says I'm going to 2 from the left. So let me get rid of this one. So now what I'm going to be doing is I'm going to be coming in towards 2 from the left side to try to figure out this limit. Well, if I'm coming into 2, you can see that my function values are all down here, and it appears that they're heading towards whatever that value is there, and I'm just going to guess that that is getting closer and closer to 2. So my estimate for this limit is I get 2. All right, well then let's try this other one. Let's go to 2 from the right side. So this is called the left-hand limit. This is called the right-hand limit. So from the right side, or the right-hand limit, as I come into 2, now all my values are up here on this part of the graph. And as I get closer and closer to 2, where are my points going? Well, it looks like they're traveling down this graph, and they're going to end up close to that point. So what's my answer? Notice that the function's down here. It's undefined here. That's what the open circle means. But also remember from the definition limit, I said we don't care if the function's actually defined or what it's defined to be. We're worried about where the function is going. So as I come into 2 from the right side, I'm traveling along this graph. My values are heading towards, it appears they're getting closer and closer to positive 2. Down here I should have said negative 2, sorry. That was my mistake down here. But these look like they're heading closer and closer to the value of 2. So I would estimate this limit to be positive 2. Well, now we're trying to put it together to say, well, what is my actual limit as x approaches 2? And so this one uses both sets of arrows. I'm coming from this side, I'm coming from this side, and the question is, what's the value of the limit? So here are my options. I came up with negative 2, so maybe I've got negative 2. I came up with 2, so maybe the answer is 2. So from one side I got negative 2, that was from the left. From the right I got positive 2. The function is defined to be 2. I keep getting that mixed up. It's defined to be negative 2, so maybe it should be negative 2 because now I've got the limit going there and the values too. Or maybe it's both 2 and negative 2. So maybe I can do negative 2 and 2. Or maybe I just have to say if you can't pick one, then it's neither. So I've got 4 choices here. Is it this, both, or neither? Well, to help us out, there's a theorem that says this. It says that your actual limit from where I don't specify a side, which means when I'm approaching C here, when I don't specify a side, that means I've got to be jumping back and forth from side to side, only equals L if both the left and right hand limits equal L. And now this says if and only if, which means it's equivalent. It says if my limit is L, then both of these are also L, and if both of these are L, then my other limit, the actual two-sided limit, is L. So if and only if means equivalent statement. So going back up here, I can't say that the limit is negative 2 because both of these left and right hand limits aren't negative 2. Same way I can't say it's 2 because both of these aren't 2. I can't say it's both, because for it to be both, they would both have to be both -1, -2, and +2. So my only thing to be able to say is, well, it can't be either of these or that. It can't be any of these three, so it's got to be neither. Or what we'd say is this limit actually does not exist. That's our abbreviation for does not exist. So it turns out if I'm coming from the two opposite sides and my graph is not matching up, the limit won't exist. So if I'm looking at a limit and I say that the limit is 2, then when I'm coming from the left and when I'm coming from the right, no matter how I get there, they have to end up at the same point if I'm saying that limit's 2. And that's not what's happening here. The limit is not, both sides of the graph are not approaching the same value. So that limit is, that's how we say a limit does not exist. So in a graph, it's pretty obvious where a limit doesn't exist. You've got a big break in your graph. From one side, you're approaching a value. From another side, you're approaching a different value. You don't have just a little hole in the graph. If you have a hole in the graph, that limit's still going to exist because it will still approach the value that where it should be, even though it's not there. That's where it sort of should be, is what you're thinking when you're saying that's the limit. So that's the idea of another way to evaluate limits, is to look at the graph and then use the graph to help you see whether the limit exists and what that value is. And then we added this new notion of left and right hand limits that we'll also have to use on occasion.